So, and I would also like to thank Parker's system to let me have the opportunity to speak here. I'm very excited to see all the features that AFM can have, especially as a senior postdoc who is dreaming about starting a new lab someday. Okay, so for my research, I'm a chemist by training. So, and also I use scanning tunneling microscope, a very similar tool. We are interested in heterogeneous catalysis and surface structures and how that can give us more insight into chemical reactions. Let me have a brief review about what catalysts mean. A catalyst is actually, in the very beginning, if you have a reaction, the reactants needs to go over energy barrier in order to form products. But with catalyst, it can lower the reaction barrier, so this reaction can occur more efficiently and faster. In heterogeneous catalysis, that will happen by interacting between molecules and substrate. It will absorb, diffuse, interact, and form products and leave. So in real time, actually, only certain areas of the surface are active. Not all the surface areas are active. For example, here is the Fischer-Tropsch reaction. You see only here the defect areas are the active sites to form molecules. So in my research, I'm interested to see how this surface structures, especially at near atomic level, can affect these chemical reactions. And today, I'm going to use chemistry reaction about methanol oxidation as an example. So on the left is showing some spectroscopy demonstrating that reaction can occur and what products are. So basically, they freeze the methanol on the surface at really low temperature. The surface already have some oxygens on there. So as they increase the temperature, at certain temperature, the energy is enough for the reaction to occur, and you will see the intermediates and the products forming. The products were detected by the mass spectrum. So here, you see the formic acid is forming as a product, and also some other products. If you see on the right, the schematic is showing as animations. So the methanol will absorb on the gold surface, react with the oxygens on the gold surface, give you a hydroxyl and methoxy. This is the intermediate. The methoxy can keep reacting with hydroxyls or oxygen add atoms, give you formaldehyde and methylformate as a final product. This reaction is very selective, especially at low oxygen coverages. Almost 100% of methanol reaction, after going through the reaction, will give you methylformate. So I'm going to use SPM to see the surface with oxygen-covered surface and see how that surface structure can evolve during this reaction. I particularly choose to study at room temperature, so all of these intermediate reactions are not visible in SPM. What I will only see is the oxygen structure and how that will change. Okay, we're starting with gold 110. This is the top view, this is a side view of the surface. It actually have a zigzag and have tunnels of gold. When we absorb oxygen atoms on the surface, the oxygen atoms will form these zigzag structures. In the real STM image, the color corresponding to the apparent height, the oxygen actually is imaged as dark features most of the time. And these dark lines along the gold rows are oxygen chains imaged with STM. These oxygens does not want to be isolated by themselves. They want to stay side by side as chain groups. So this is a schematic showing how chain groups look like. These oxygen atoms form side by side together. And with this structure, we have some terminal oxygens, which are oxygens on the very end of the oxygen chains, and side oxygens, edge oxygens, which are oxygens on the edge of these chain groups. Okay, with this surface, I'm going to expose methanol at room temperature. Very low amount of methanol, though, is like a 9 and a 10 to the minus 10 millibar. It's already after background subtraction. Okay, so now we have two different terraces. The light yellow one is upper terrace, and the red one is the lower terrace. So after I start to dose methanol, here is the time I'm dosing. In the very beginning, not much is changing. It's like induction period there. And after a while, it starts to react, and some of the oxygen chains start to disappear. And eventually, after a while, all of the oxygen chains will be consumed, and what's left over will be just a clean gold 110 surface. If we take a closer look during the reaction, we found that a clear area about rectangular shape on the terrace, and that actually indicates the reaction rate is not uniform. The reaction or the oxygen wants to be consumed is preferred to be consumed along the row direction. I can measure the oxygen consumption rate along the rows and the cross rows, and along the rows we have about twice more reaction rate than the one across rows. Now we think about why it can happen, what's driving this phenomena to occur, and also is this something about methanol or something about surface we have? So we did another experiment using a very similar alcohol, isopropanol, to react with the surface at similar conditions, room temperature, and we saw the same thing, the rectangular shape come again. So we can now ascribe this feature to something about substrate, something about surface itself. You may think about, okay, we have tunnels. These molecules want to absorb on the tunnel on the surface and diffuse more easily along the tunnels. That could be obviously one of the possibilities. But there are other things we can consider. For example, the oxygen chains on the surface. When these oxygens form the chains, the binding energy, the stability of the oxygen on the terminal side is different from the oxygen on the edge side. The terminal side, if you look at these bond distance, the terminal oxygen is 0.1 angstrom longer of the oxygen gold bond compared to the one in the center. So 0.1 angstrom seems to be very small to you, but for oxygen atom it's actually big. So these terminal oxygens are less stable than the middle ones, so they are easy to consume. And once this is consumed, the middle ones now becomes the terminal one, so they can chew along the row direction. The other reason we think about is the surface strain. So once the surface, gold 110 surface have oxygens covered, these oxygens can actually induce the mismatch of the gold that binds to them. For example, that gold, which bonds to two nearby oxygens, have increasing about 70% of the lattice spacing along the rows, and about 0.6 angstrom lift to the vacuum. So once some oxygen is consumed, we believe the strain will be released. Once the strain is released, that also could possibly facilitate reaction to go along the row direction. Okay. And also, there are weak attractive interactions between these oxygen chains. Some oxygen chain is consumed completely. We break these weak interactions, and that can also be another factor. With this in situ or in real-time measurement, one advantages we can gain is to establish these dynamics during the reaction. So this is from each STM image. I measure how many oxygen are left over on the surface. So with this plot, you can see how the oxygen is consumed during the reaction. As we said, while we're watching the movie, there is an induction period where there is no obvious decrease of the oxygen coverage. And then we move to the slow reaction period and then fast reaction period. So it's just some kinetics during the reaction. I want to look at the surface structure in the very beginning and the structure during the onset of the fast reaction period. Try to see if any surface structure can contribute to this fast reaction. Here is a comparison. On the left is in the very beginning what surface look like. On the right is the onset of fast reaction period. We can see a lot of the oxygen is already being consumed. And on the left, we have chain groups like across large areas on the terrace, well, on the right, we don't have that much long chain groups. It decomposes into small parts. So we think that decomposition actually is related to the fast reaction speed. And also that's breaking the attractive interactions between the oxygen chains. Okay, with that, I would like to conclude. Use a scanning probe microscope to study the methanol oxidation at room temperature over the gold surfaces. So we noticed the non-uniform reaction rate, which is preferred to occur along the row direction. And we ascribe that to the tunnel structures and also the active terminal oxygen site and strain release from the substrate as the reaction occurs. During the reaction, there are 3 different periods: slow reaction periods, induction period, slow reaction period, and fast reaction period. So what we found is that these change of the surface structure, both atomically and mesoscale structure, can be dynamic during the reaction. And that can actually influence the reaction rate as the reaction develops. With these insights, we hope that understanding can contribute to the designing and optimize gold-based catalyst for selective oxidation reactions. I think I did a really good job in saving our time for dinner. So, and I'm also fine if there's no questions after this, we can discuss in more social times. Yes. Yeah. Oh, I forgot to mention the research has been supported by DOE. Yeah. Okay. Yes.
Do the rows go across the terrace too?
The oxygen chains. Yes, so it does not seem to be, the step edge does not seem to affect the growth of the rows. Yeah, because if you look at the structure of these oxygen chains, it's really just absorbed on the edge of the rows, right? So once you have the step edge, the top terrace will have these edge structures, rich structures of the gold, and lower terrace will also have the rich structure of the gold. So it does not really affecting the formation of the oxygen chain, although there is a step edge. Yeah.
I have a quick question.
Yep.
How do you measure the strain? You said
yes, so the strain release is actually not, I cannot measure it. We look into literature, and there are theory calculations on a very similar structure. They have oxygens absorbed on the, I think, palladium 100, very similar structure. And they, theoretically, they calculate their strain related to that. So once the oxygen is no longer there, the surface goes back to the most stable structure, and you don't have that strain anymore. So once these oxygens are consumed, we say there is a strain release.
Your structure gold is always 110, and no matter you have oxygen or no matter you have methanol.
Yeah, so that strain is actually due to the oxygen absorption. So once we have the oxygen, we have the strain. Once the oxygen is reacted, is consumed, we don't have the strain anymore. Does that answer your question? Okay. Yeah. Yeah, I'm an experimentalist, not theorist, hopefully. Okay, thank you.